And 2 in the morning. We're going to get started with Grigorios Chrysos from Madison. He's going to talk about towards sequence-to-sequence models without activation functions.
Thank you, Sasha, and the organizers for inviting me. Thank you, everyone, for being here early in the morning. So I'm excited to talk about this new work that we've been working for a while. And this topic without activation functions is a topic I have been working for some years already. And essentially, this topic is a little bit different than the previous talks, right? So that would mean that I did what every person would do in an LLM workshop. I went and asked an LLM what it thought about the title and what essentially it would imagine the title meant. And this is what I got as a response, which is not pretty bad. It is pretty good. And in fact, many of the core components that this LLM has are right. So it imagined that we can get the expressivity from polynomial expansions or equivalently multiplicative gating, that we need normalization, and of course that we have input and output matrices. And in fact, this is almost right if we don't observe this sigma, until we observe that sigma. So it kind of inserted an activation function there, right? So it is one way to obtain expressivity, but I'm going to argue that is not unique. So what I'm going to do in the rest of the talk is try to build networks that are expressive without using activation functions. And essentially, let me firstly thank a lot of amazing colleagues that I have had over the years and have helped me formalize many of these concepts, and especially the Madison team, where Guillaume and Linux have done amazing work on this topic of the second part of the talk. Right? So let me start at the beginning. A few years ago, people were benchmarking architectures mostly or predominantly on ImageNet recognition, where the idea is you have an input image and then you have one output class to predict from a set of predefined classes, right? And in fact, one could argue that the very resurgence of neural networks can be attributed widely to AlexNet moment back a decade ago, right? So given that few architectures have had tremendous impact on both ImageNet classification and the wider field of machine learning, it's only reasonable to think that essentially architecture design lies at the core of what we will be designing the next few years. And I think this fits very well with the theme of this workshop. And one way, again, to do this without activation functions would be to use polynomial expansions, which are very expressive on their own. And this is not a new idea. It has been used for several decades already, at least since the 80s. And some of these works, for instance, LSTM, are still around. But many of those work either don't scale to modern large networks or use activation function. So essentially, I'm going to try something a little bit different than these works, which is to start from the beginning. Right? So what do we do in machine learning? We try to approximate an unknown function G star where we have an input vector and an output vector, right? This is by default true even for neural networks. The difference now is that I'm going to ask an undergrad that just took their basic calculus classes and math classes, and what I hope they can say is, I'm going to use a polynomial expansion, right? So this would be essentially the first order terms, right? Which is essentially even the base of all networks that we are using essentially linear layers. But what I want to do now is include second degree expansion, where we have xi, xj pairs scaled by this learnable parameter w, and essentially continue until very, very high degree expansion. And essentially, this is nth degree, and you see n summations here. And equation 1 is very, very general. It can express any polynomial expansion. And essentially, I did this only for the t output, but I can build the polynomial expansion for any single output. And it's all good until I realize that these learnable parameters w and even more here scale really badly with the degree of expansion. For instance, here, even for the t fixed output, we have I and j that run 1 over d, which means this is going to be a third order tensor of dimension d squared times the output, right? And if you imagine for nth order, this is going to be really, really huge, which means that it cannot fit in modern GPUs, given that d, which is the input dimension, is something that runs in hundreds, thousands, or even tens of thousands nowadays, right? And maybe in a few years, we will have bigger GPUs, but I think until then, we will also have bigger data. So the question then is, how do we solve this problem right now, where we can scale down these parameters without losing essentially the polynomial expansion of equation 1? And I must say again that this is not something that hasn't been thought in the literature. In fact, there is a wealth of architectures that have already kind of skipped equation 1, but directly gone to the polynomial part. For instance, here you can see LSTM captures just multiplicative interactions, right? It has a Hadamard product, or essentially non-local neural networks, which are popular and self-attention, particularly the encoder part that are third-degree interactions, or even the popular style gun architecture, which is one of the most successful generative adversarial networks. So before diffusions were cool, this was state of the art, and it's still one of the most successful generative models I know of in images, right? So the generator of that architecture is essentially a polynomial expansion, and it looks something like this, right? And in fact, historically, this is how we started looking into the problem. What does it mean it looks like this? Well, here I'm going to transition to the equation in the next slide, but here let's stick for a second to this schematic, because I believe this can give a first idea about what is happening and why this is a polynomial expansion. So here we have our input x and our output f of x, and this looks roughly like the schematics that you likely see in neural networks nowadays, right? So then the question is, why is this a polynomial expansion? Well, let's start from the left side, right? So we have an affine transformation W1x, which we name y1, just an intermediate term, right? And then what we do is we do 3 operations. We do a linear transformation again with the input. We do a linear transformation with y1, and then we do a Hadamard product, where Hadamard product is essentially element-wise product, right? So we take the ith element of the first operand, the ith element of the second operand, and this gives us the ith output element. So this is essentially a second-degree expansion, right? Why? Because we have an x here, and essentially y1 was w1x, so we have another x here. So it is some form of the equation 1 that I showed above, but what I have hidden here is that this is a more constrained form of this equation 1, because I have implicitly assumed a CP decomposition. This detail is not really important, but it is important that y2 is essentially a second-degree expansion. And we can proceed like this for third-degree expansion, where again we do these same 3 operations. So the first one is w3x. The second one is we take the previous intermediate term and then we do a linear transformation. And then we just have the Hadamard product of the 2. And then y3 is essentially a third-order expansion, and I promised a third-order expansion, so I'm done. So what we are going to do in the end is just a linear transformation of this y3, and we are done. I promised though high degree expansions, and third degree barely registers as high degree, right? So the question is, does this generalize? And the short answer is yes. There is nothing specific that I shared before that doesn't generalize. So essentially, if we have a linear transformation Wn of x and a linear transformation of the previous intermediate term, we can, and we take the Hadamard product of the two, we can construct a new intermediate term yn. And if we repeat this intermediate term several times, where y1 is trivially initialized like this or any other way, we obtain an higher degree polynomial expansion. And how different is this than regular MLP networks? In fact, I'm going to argue that this is not too different. If you see the green part alone, right, and ignore momentarily the blue part and the red part, so if I have yn equals s of n, yn minus 1, and bn, this is the recursive formulation of a linear neural network, right? So if I plug in an activation function here, I can obtain a regular MLP, for instance, in a recursive format, right? So essentially, we're not too far away from MLP networks, but we don't have activation functions as I promised. And essentially, we have this Hadamard product, which gives us expressivity. And now the question is, hang on a second, what are these Wn, Sn, Bn, C, and beta that come up all the time? Well, I'm skipping a couple of steps that I'm happy to discuss offline, but essentially these come from the tensor decompositions of equation 1 to building into a recursive formulation. So essentially all of those are learnable parameters, and we can learn them precisely with the usual tools that people are using in machine learning the last few years. For instance, gradient-based methods, SGD, ADAM, or whatever is trending nowadays. One question is, what is the degree of expansion that I'm obtaining here? Or in other words, if I want 10th degree of expansion, how many times do I need to call this equation, this recursive equation? Any guesses?
10 times up to maybe off by 1?
Yes, exactly. That's precisely correct. 10 times minus 1, which is 9 times. And in general, if I want nth degree expansion, I need to call this recursively n minus 1. Again, this is the same with neural networks, right? If I want a 10-layer neural network, I need to call this 10 times, or 10 minus 1. So the question then is, sure, we can obtain something that is a high degree expansion. It looks like the architecture that we know from neural networks, but this is not high enough degree, right? Why would a 10th degree or 20th degree be sufficient for instance, ImageNet or even language modeling? And you're absolutely right that this is not the fastest way. There is a faster way to increase the degree of expansion. And essentially, this looks like this, right? So we have a input x here. We can use the recursive formulation that we had above. But now, instead of calling this recursive equation one more time, what we're going to do is use the output of that second degree block to an input to another second degree block. These two blocks can be essentially similar, like the equation I showed above. But there is a key difference here, which is the following. Here, my input is already second degree with respect to x. So when I do Hadamard product of these two, what I obtain is not a third degree expansion, it is a fourth degree expansion. And essentially, when I do this one more time and I have a third block, the maximum degree I can obtain is 8th degree. right? So this means if I stack m such blocks, I can obtain something that is up to 2 to the power of m, right? So with 10 such blocks, for instance, like ResNet 18 has 8 blocks of residual connections, I would be able to obtain 2 to the power of 8 with 8 blocks, and then like the original convolution is first order. So this increases the degree of expansions very, very fast. And in fact, in most of the works that I'm going to present from now on, we're going to assume a structure like this, where we have sequentially different polynomial expansions. And this generalizes even better if you don't have second degree here, but third degree, then it would be 3 in the power of m, and so on and so forth, right? So we did, with these two equations, essentially this recursive equation and these sequential polynomials, a host of experiments back a few years ago. And then we showed that these networks were very, very expressive, both in image generation, image recognition. We did even large-scale recognition with 500,000 classes back then, and it was state-of-the-art actually for a couple of years. And essentially one experiment that I was really interested in and was fascinating to me was that we built this whole framework having in mind image modeling, but it extends beyond image modeling, right? So this was in meshes, so 3D point clouds. And essentially all of the baselines, since they're regular neural networks, are denoted as first order here since they don't capture higher order degrees. And we have two standard data sets where here we measure the generalization error. And we notice that the generalization error is generally going down as we increase the degree, which was a promising first result in how these networks perform even beyond what we demonstrated or we built them for. And the second very interesting thing in this experiment was that we noticed for the first time that when you didn't have activation functions, it was performing better than when you had a polynomial with activation functions. This was not the same back then for all experiments. It wasn't trivial to us why you would remove the activation functions, but this was the first indication that this was performing better when you removed the activation functions, because the expressivity was coming from the higher order interactions, essentially. And this was the end of the story? No, because it didn't work in other experiments as well, right? So when we tried to go to CFAR datasets for image classification without activation functions, it performed decently, way better than linear ResNet, but not on par with like the ResNet we know, right? So like it wasn't on par with modern networks. So essentially what was missing was the key question we have been asking since, and essentially one of the components that we noticed and tried to improve a lot was more aggressive normalization. And if you want, this is very similar to what transformers have, and one could argue that if you take out the activation functions in transformers, they have some form of the equation 1, which is a polynomial expansion, right? So given that transformers have very aggressive regularization terms, we also included these orange boxes of regularization terms, and it already performed better. But that was not still on par with transformers themselves. So we went back to the drawing board and said, okay, let's look into the architecture design again, and this is the last work we have done on images, and then I will transition into sequence models. But I'm really proud of this work. Why? Because essentially this was something that I believe resonated with a lot of other folks on the power of polynomials in modern era. Why? Let's see what we did first. We went back to the drawing board and saw that people, the way that they're doing image classification the last few years, for instance, with vision transformers or MLP mixers alike, they are just chopping the image into non-overlapping patches and processing those where usually here is a transformer. We removed the transformer and we wanted to plug in this polynomial expansion. And what is this polynomial expansion? Well, this is essentially what I showed before of blocks of degree 2, which we named new layer here. There are a lot of details here that are not super important since they are essentially linear layers. So for instance, here this is named channel projection, but it's just a linear layer, right? So you see here there is one Hadamard product, so this is essentially second degree interactions. And we repeated this block twice where there is just this red block missing from this second one, otherwise they're exactly the same. And then we repeated these two blocks many, many times, again in the sequential polynomial form. So the question then is, what is this red block? This red block is just something, it's a standard tool in the literature for image recognition, which is just inserting noise in the 3D tensor. And this was a regularization format, if you want. And just to show you why I was really proud of the results we were obtaining. So these were, this is standard ImageNet classification accuracy table. And essentially, ResNet 18, which is the by default benchmark, I think nowadays was around 70%. And you can see that previous work that we had done were roughly reaching that 70%, but they were not on par with transformer-based models of like 78%. And essentially, this last work did manage to reach that performance, right? So I'm really, really proud of this work that was published last year, since it is the first work that we managed to remove element-wise activation functions, right? So essentially, there is no single activation function, as we also declare here, right? No ReLU, no softmax in the middle of the network, no GeLU or whatever other people are using nowadays. And it was reaching performance on par with transformers. You might argue transformers are already a few years old. Sure, but this is already, I think, an important benchmark to hit on. And this was something that was very interesting, but then the question is, sure, but how applicable is this architecture? Because we know from essentially our analysis classes and math classes that if you have a little bit of noise, right, and you expand it into high degree of expansion, that might blow up. And we did try in that same paper to extend the results and see the robustness on this ImageNet C, which is a standard data set. It's ImageNet corruptions. And it has some popular corruptions on noise, blur, weather, digital, so on and so forth. There are some more corruptions. And essentially, this is a lot of results. But what this says is that it's not too bad. I consider that it's on par with many of the other competing architectures, including these two vision transformers or ResNet, where here we are measuring the mean corruption, so lower is better. And essentially, from these results, you can see that it's slightly better, but I want to think that it's not worse. That's the important point here, right? So how is this happening? Actually, open question for me. Why is this happening, and why does the high-degree polynomial expansion doesn't blow up with these corruptions? I don't know the answer. I just asked the Yisin to do the experiments again to make sure that we didn't make a mistake, but the results were very similar. So I think the regularization, which is the usual normalization techniques, and essentially the learning itself is somehow implicit bias here. But I'm really interested and curious to know how these networks are similar on par with other networks in terms of like this benchmark. So essentially now transitioning from these formulations into three applications that I'm going to move rather fast, right? So the first one is that this architecture, even though we build it for a single input, single output, can trivially extend to multiple inputs and multiple outputs, right? And what is one application of this? Well, again, back before diffusion was cool, we were doing a lot of conditional GANs, right? And we thought, why not do a conditional GAN where you have, apart from the Gaussian noise in the generator, you also have, for instance, some input label, right? So you know what class you want to generate, or you have an inverse problem, a corrupted image, a low resolution image, and you want to scale this. So we modeled essentially the generator of these generative adversarial networks using a polynomial expansion. Essentially, equation 2 is very similar to what I showed before, and this network is essentially the equivalent of equation 2, just in a little bit more schematic format. And it turns out that you could use it, and I'm not going to focus too much into the results. There are plenty of experiments with conditional generation, class conditional generation, attribute conditional generation, and inverse problems in that paper. Another interesting perspective of these polynomial expansions was that in 2021, there was an oral in iClear which was saying that ReLU neural networks outside of the support of the training data are linearizing, right? So in the out-of-distribution regime, in the extrapolation regime, ReLU networks linearize. And when I saw this paper, I found it really fascinating. I was like, hang on a second. We rarely want to predict linear functions even in the extrapolation regime. And this is a benefit that I thought intuitively these polynomials would have, and then we proved in that paper that indeed they do not necessarily linearize, right? They can extend and expand, follow a gamma degree polynomial expansion. And this was precisely what we showed here. Okay, the colors do not show really clearly, but essentially these red points are the extrapolation regime, and this NNHP was neural network with Hadamard product, so these polynomials I'm referring to. So here you would see that, like, if you have a known ground truth function, that these networks kind of extrapolate better than ReLU networks that indeed linearize in the second and the fourth case. And you might say, this is synthetic experiment. I agree with you, and this is why, like, we extended to other standard benchmarks, which was visual recognition, for instance here, visual addition, sorry, where you feed in one MNIST digit and another MNIST digit, and then you expect their addition to be the output. And this is a standard benchmark that some of the pairs are not seen during training at all, removed, right? And what we noticed was that the results were improved when using this architecture design. And even though I've been interested since in this extrapolation regime, we haven't done too much work. And I think there is a lot of interesting extensions here, for instance, on domain adaptation, where people care about shifting the whole distribution of the data, or even, like, from the theoretical perspective of certifying what function can be extrapolated here, right? Because we have an analytic expression, or potentially we can derive an analytic expression. And last, since we are here where there's a lot of theoretical tools, theoretical talks, one benefit of these networks is that we found that their derivations are generally easier, right? So for instance, it's a little bit easier to derive upper bounds, lower bounds, for instance, Lipschitz constant or Rademacher complexity that we have done, because exactly you are missing these activation functions, which you need a lot of conditions usually to bound those, right? So I think this was a one-page proof for arbitrary degree, which I cannot say the same for neural networks that is as easy to do. But since we are here for the part of sequence to sequence, let me transition into the second part of the talk. So essentially, I'm going to focus on this specific problem where we have an input sequence, right? The two numbers here, and we want to add them. Of course, this is not only related to addition, you can do additional tasks, but essentially in sequence-to-sequence models, you feed in this input, and then your model predicts one token at a time. And here it would be 5, 7, 9. And there is a lot of work on this domain where I was motivated on this by my awesome colleagues Kanguk and Dimitris, who figured out that actually this particular thing, when you try to learn it with a transformer, it's getting harder when you don't use reverse order. Why? If you think it for a second, essentially the way we do addition is that we add the least significant bits to know if there is a carry, right? So like if there is a carry, we're going to increase one of the next digits. So it is easier for a model to predict the least significant bit first and then move in the other direction. So this was a paper that was published last year, and there has been a lot of work since on improving that. What was the purpose of this? This is a toy task, right? But people have been wondering why transformers cannot do these tasks, right? When people famously have been going on ChatGPT and asking very simple 9 plus 5, or more recently with more digits, or very, very simple operations. And you are like, how is it possible that they cannot do this? And more generally, to figure out what is the inductive bias and how do these models learn in a more controllable setting, right? So what the authors here are trying to do is trying to figure out how you can improve on this task, essentially, and what does this mean for training these large language models, right? So one of the key findings so far has been that the vanilla transformer might do better when you do this reverse addition, but it does not figure out the algorithm of addition itself, right? So one of the key efforts here was, can we do 3 and 3 digit addition during training and then do 10 and 10 digit inference, right? And people have figured out some ways to do this is through modifying the embeddings and essentially hard coding the positions, or looping through transformers and iterative training. And of course, all of these efforts have been really good to figure out the inductive bias transformers. But again, coming from the perspective of no activation functions, we're going to try to tackle this task without activation functions, right? The setting remains the same. And what is the setting? The setting is exactly this. We have an input that is 2 operands, 2 numbers, usually multi-digit, and then we want to predict 1 token at a time, and all of these tokens to be correctly identifying the result of this addition. And of course, this task is not the only task. People have been developing architectures the last few years. There's a lot of work on efficient transformers, state space model, recurrent architectures, or hybrid architectures. And I'm pretty sure there is a lot more work coming up soon here. I think it's a very interesting area and many interesting problems here. But again, I'm going to focus a little bit on the transformer part. I apologize, this is the one slide of notation, right? So this is Hadamard product. We discussed of Hadamard product between 2 vectors, but in reality, this generalizes to arbitrary tensors, right? So I'm going to add any element and the corresponding with exactly the same indices element in the second operand and obtain the same index for the result, right? And then we need 3 different symbols, n, m, and d, where n is the sequence length, right? Remember, we are trying to add 2 numbers. We have a context window, and then we have an embedding dimension, our feature size. So with these 3, we can get to the formulation, which is we have our input sequence, n times d, right? So we have these 2 numbers. We extract the embedding dimension, each token d-dimensional, and then we compute two linear transformations, O and phi, and through phi we format this tensor P. How? Well, we take phi, and each row of this we are going to name phi I. So phi 1 is the embeddings of the first token, right? So the features of the first token, right? So think of the first digit that we have in our input, and we extract the embeddings, the features of that. This is phi 1. Phi 2 are the tokens of the second input, and so on and so forth, right? So here you will notice that the pattern is as follows. We have phi 1, phi 1, phi 1, blah, blah, going all the way down to the main diagonal. Then we have phi 2, blah, 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 phi 2 here, and so on and so forth. Why is this structure? Well, for all of you that are familiar with essentially the causal structure of transformers, that's essentially the same that we are trying to leverage here. Why? Because in next token prediction, if you want to predict many, many tokens as output, you need to compute the loss once and then recompute given the new updated sequence, and so on and so forth. And this would take several iterations, right? Especially for long text that we want to generalize nowadays. And therefore, what we focused here was to have the same causal structure that essentially would enable us to do the masking that people are doing in language models and do this in one forward pass during training. And why is this a tensor? Because we have n input digits and we want to capture features in this dimension. And remember, each of the phi I is a vector, is a d-dimensional vector, right? So that would go perpendicular in this dimension. So we have the tensor P, and now we are going to make a Hadamard product of the tensor P with the tensor O. What is the tensor O? O was a linear transformation of our input, and then we format this in a tensor, and we obtain this tensor T, right? So equation 5 is essentially showing a random element of this T. I'm not going to state too much here because essentially the next equation, I think, is the final output Y, which is just summing T in the dimension of the context length. And even though the details here are not really critical, we made one convention here where phi I is the zero vector when I is negative, just for not making equation 5 more complex. And essentially the most important thing is that this yik, which expresses my ith output, is a second degree expansion. Why? Because I have xiv and xi minus j plus 1 here, right? So I have x and x. So essentially equation 6 is not that different from what I was showing above in the previous works. We just have the additional overhead of equation 4 of the tensors for having the causal structure. And since I know equations can be burdensome to look, let us look this from a little bit more abstract format. So we have this original input phi matrix, which is features of our input tokens, right? So phi 1 are the features for the first token, phi 2 for the second token, so on and so forth, right? And then we format this P, which again has this phi 1 in the main diagonal, phi 2 here, phi 3, phi 4, so on and so forth. We format the second tensor, which is another linear transformation of our input, and we essentially copy it d times, where d is the feature size, y, such that we can do a Hadamard product, right? So this was a linear transformation of the input, so we have nm, which was the O, and we repeat this d times, right? So we format another third order tensor. And then what do? We do the simplest thing, which is Hadamard product of these two. Again, what is the Hadamard product here? It means I can take the ijk element of that tensor and the ijk element of that tensor, and this gives me the ijk element of that tensor t. Are we done? We have one more step, which is to sum over this dimension m, right? So we had n tokens and d features, right? And that's what we are left with when we sum over m, essentially. And this is the output that we are obtaining that, again, expresses second-degree interactions. And let me transition into some results here. What can we obtain? So we trained this on 3-digit operands, right? So 1, 2, 3 plus 4, 5, 6. And what you see here is the comparison with the vanilla transformer, right? There are a lot of improvements, again, that people have done awesome work there, but we wanted to compare with the vanilla transformer here. And what you see is the number of iterations here on the x-axis and the test accuracy on the y-axis, right? So ideally, we want to be in 100% accuracy in 3-digit addition when each operand is a 3-digit number. And there are two modes for each experiment when we have reverse C, which means we reverse just the digits of the result, right? The LSB first that I mentioned, or when we also have reversed all of the digits. And the results are pretty consistent in both cases. Namely, here you see the orange curve for transformer. When we reverse only, the result is slightly worse than when we reverse all the digits, and it's the same for the polynomial. And there are two interesting things when you compare these two models, right? So the first one is that the polynomial seems to require less examples to increase in terms of the accuracy, but at the same time, when the transformer reaches 100%, it reaches this quite faster because the polynomial is uncertain from 300 roughly iteration to till 1000. But at the same time, both of them manage to reach 100% accuracy after a few iterations, and essentially this is a model that doesn't use, again, activation functions. And the most impressive part is that this polynomial expansion uses half of the parameters of the transformer, which I think this is a standard model that people that are doing this task are using. And you could use this with half of the transformers. And in fact, many of these observations are consistent with what we had in previous work, which is, and there is like also some theoretical work that these polynomial networks can learn faster than regular networks, but at the same time, they might need additional regularization. And there are already some results on expressivity showing that they can be a little bit more expressive. And we thought, okay, let's challenge this a little bit more. And what happens in extrapolation, right? Does it learn the true addition algorithm or not? And we figured out that the previous experiments for the transform is already known that it doesn't learn it. It seems for the polynomial it also doesn't learn it natively. So we did one modification, which is the following, right? So we had these original numbers to add, and then we zero pad if necessary. We reverse the numbers, and then we add some random spaces. And it turns out that this is sufficient for both models to extrapolate way better. So here you can see that we have learned up to 30 digits. So each operand is up to 30 digits. And then we tested way, way more. I'm going to say that none of these has learned the true algorithm of addition, right? Because I don't think any of us in school learned 30-digit addition, right? We learned in 1 and 2 digits, and then we could extrapolate, right? So these do not seem, neither of these models seems to be data efficient, but still they do show a little bit of extrapolation performance, especially when used with this augmentation method with the spaces. And in fact, for some reason, this transformer model is going down a little bit faster after you cross 60 digits, while this one without the activation function seems to be a little bit more robust. Again, it's the same model where we have half of the parameters. And this is essentially some of the latest results that we have, where I'm going to say that this can expand to other tasks, and we're currently working on this, but this is something that shows, right, how you can indeed learn without activation functions on these sequence-to-sequence models. And yeah. So that's a very good question. We were trying to figure out what is the reason that other augmentations do not work, right? So like people have, if I go all the way back to what people have proposed here, all of these modified embeddings in transformers only worked in transformers and no other architecture that we have done, right? So for instance, in this polynomial or other architectures that we tried, they don't work. These loop transformers is for transformers. So basically, we were trying to find out what would be a universal augmentation that works well beyond transformers, right? So this data augmentation actually came when we saw this formulation of the transformers, and I think the credit of that goes to Linux, like one of the students that I mentioned earlier, where she noticed this I minus j, and she was like, oh, this is kind of like learning some relative positioning. So if I insert these spaces, I'm going to obtain additional performance. And it seems that this works also on vanilla transformers, which is pretty interesting. Any other questions? Yeah.
So does this mean that it can handle like length generalization as well?
Yeah, this is essentially length generalization, right? So like we train up to 30, and then we essentially test way more digits during test time.
Yeah, but it's eventually going down. I guess what is weird to me is that if it's going eventually down, that it's not really learned accurately.
Yes, I agree with you. None of the two has truly learned the underlying algorithm of addition. And in fact, they're also very sample inefficient. So I think if you reverse this on its head, it says we have a long way to go, even for learning simple addition, right? So I think this is the interesting part here. Yeah?
Also, like the polynomial version doesn't seem to go down too much. So maybe there is just a class of problems that is hard for it to add. There is another class of problems that is easy. Did you see some such cluster of problems that were just harder because of some inherent reason?
So I'm going to say, I agree with you that like polynomial does seem to be above 90%, which for 90-digit addition is impressive. But I'm going to go that like it hasn't learned the true algorithm. It's very close. So we don't know. We're actually working on this. If it can get and learn the true algorithm for any arbitrary digit, I'm going though to make a prediction that like for both models, they're starting to go down when like some of the hyperparameters is hit. So for instance, in the polynomial, I know that it is affected widely by the context window length, right? So this M parameter. If we had like GPUs that could fit M to be very big, it would essentially improve the result. But M being, I think, less than 100 means that like it cannot account for like very, very big, given the data augmentation as well, right? Like for very big context, right? So that's, I think, one of the critical reasons that it is going down here, but it's still, the result is the same. It hasn't learned the true underlying algorithm. Yeah?
I just wonder, have you tried now go from 0 to 30, but maybe do some more stratified way in constructing your training set?
What do you mean exactly?
Like for example, I can take 0 to 10 and then 30 to 40 and then so on. So you can leave out, you can still count as generalization?
We have tried, and the results there are a little bit interesting, where this polynomial seems to be a little bit more robust than transformers. We're actually working this month to put out the archive paper, but essentially you are correct that there is a little bit of difference. Both of them are going down though. But it seems that the polynomial, for some reason that is unknown to me, is a little bit more robust there, and we're currently exploring this, but a very good question. Yeah.
One down question. So could it be because of the positional embedding are not learned in the transformer when you do like go very long? Or it has nothing to do with the learnable positional embedding?
So I think we have tried both versions in the transformer. We didn't see any significant difference.
Sorry, when you say try both, you mean?
So with learnable embeddings, without, not learnable positional encodings, that's what you're asking, right?
Positional embeddings.
Positional embeddings. I think we did try that, but I'm not going to be 100% sure. I know for the polynomial we did try when you don't have learnable positional embeddings. The performance is slightly worse, right? Because like you're essentially not learning this dictionary of embeddings. So I think in both cases the results would be worse, not better. If you
like the core problem that we don't learn this positional during training, and that's why it fails to generalize to those positions.
But we are learning. We are learning them. Both models have learnable positional embeddings.
But you never see those long positions during training.
Yes, you are correct. It might be the case. But yeah, this is part of the inductive bias where like we haven't figured out even for this simple problem. Right, so essentially let me zoom out since my time is running out soon and say that like all of these polynomial expansions that I focused, we have been so far using standard learning algorithms, for instance, SGD, or standard losses. People are using standard regularization and normalizations, but there is no reason to think that there aren't any better techniques to optimize them or regularize them, or even better tensor decompositions, right? So like so far what I have showed, I skipped the details, but they all rely on the simplest of all tensor decompositions, CP decomposition, right? Which is like a blatant, just low rank decomposition with very little structure. So I imagine there might be way better ways to do this. And in fact, I'm really, really curious for all of the problems above, if we could study and find a sufficient degree of expansion, right? With a neural network, you are like, let me throw 10 layers, 20 layers, who knows? But now with the degree of expansion, can we say something about the degree of expansion? And what does this say about the robustness? That we just did this little experiment and showed that it's not too bad, but essentially how good is it is unknown, right? And have this schematic just to say that like I focused in some works on these polynomial networks, but there's a lot of other exciting work, including about their theoretical properties, universal approximation, for instance, or how you can use this perspective of polynomial expansions to change the matrix multiplication to Hadamard products, and this would enable you to have linear complexity in transformers, particularly when you are doing image modeling, or the spectral bias that I mentioned, that they learn higher frequency functions firstly. So there is essentially a lot of work on both the theoretical front and the empirical front. I think my prediction is that in the next few years, there will be a lot of exciting works in the intersection here, because we do seem to know a little bit about the theoretical part, a little bit about the empirical part, but some more principled designs would be ideal. And with that, let me conclude that essentially what I tried to argue today was that high-order interactions, right? So if we have polynomial expansions, might be sufficient for extracting representations. Essentially, I think this area can take a lot of new architectures and a lot of theoretical or empirical analysis, right? We know very little, I think. And again, I'm really happy that some of the speakers throughout the week mentioned the same about diverse problems. I think there is a lot to explore there. And in fact, let me close with one key question. Even if these polynomial networks do not take off, which is something that might happen, I think if anything, there is one thing that I try to argue today, which is, what do activation functions truly offer, right? Do we really, really need them, or are there better ways to obtain expressivity? And with that, I'm going to conclude with this interesting imagination of how Microsoft Copilot imagines me giving a talk in California. Clearly, we have a lot of work to go. Thank you. Any questions?
Okay, let's thank the speaker again.
Thank you.
Cool. Yeah, the next talk is at 11.